We have talked about an iterative pre-order traversal that requires big O of n time and big O of n auxiliary space. Let us now talk about an space optimized solution. This solution also requires big O of n time but works with big O of h extra space, where h is height of the binary tree. So it takes less space compared to the previous solution. Let us see the space efficient implementation now. The idea is to only store right children into the stack, not the left, because we know that we are anyways going to the left first. So while going to the left, we keep printing them and we keep storing the right children into the stack. That's the idea. So first we create an empty stack, then we push 10 into the stack like the previous solution. And what we do is we keep on going left, and while going left, we keep on printing those nodes in the same order, and we keep on pushing their right children into the stack. So we begin 10, we print it, we go to the left side, but before going to the left side, we push 30 into the stack so that 30 can be processed later. Now when we are at 20, we again push 50 into the stack and print and then go to 40, right? When we are at 40, we push 80 into the stack and we go to 70. So initially you have only 10 into the stack. Then what you do is you print 10, 20, 40, 70. And while you are printing them, when you printed 10, just after that you pushed 30 into the stack. When you printed 20, just after that you pushed 50 into the stack. When you printed 40, you pushed 80 into the stack. So this is how our stack looks like after the first iteration. Let's see the implementation. We have created an empty stack. We have pushed the root. Then we initialized current as root. Now we are running a loop while stack is not empty. And inside this loop, we have another loop. And what this loop simply does, it keeps on going to the left side. And before going to the left side, first thing it does, it prints the current node. Then it pushes the right child into the stack if right child exists. And then it goes to the left. Right? So keep on going to the left, and keep on pushing the right children to the stack. While going to the left, keep on printing the nodes also. Because in pre-order traversal, we always know that we need to print left first, right? So that's what happens after the first iteration. Now when we reach 70, we notice that 70 left is null. So we come out of this inner loop when we run it for next item, right? Because this current is null. So we come to the else part. In the else part, what we do is we simply take out the right child of the previously processed node. So we are going to get 80 from the stack, right? We get 80 from the stack. We print 80 on the output screen, and then we see, does 80 contain any left side? Since 80 does not contain any left side, we did not go into the into this inner loop. Otherwise, we would have gone into the inner loop. For 80 also, we have processed its left children, then its right side, right? So 80 is printed, then we take out the next item from the stack. Next item is 50, which is right child of its parent. Then we process 50 in the same way, right? So we go to the left of 50 and we keep pushing the right children. Since there is no left, we simply push 90 into the stack. So we have printed 50 on the screen and we have pushed 90 on the stack. Now we take out next item from the stack, which is 90. We print it, right? And since 90 does not have any children or no subtree under 90, we do not push anything into the stack. Now we have only left 30 on the stack. Let us now see implementation of the space optimized approach. In this approach, we are going to process left, right? While there is a left child. And while processing left, we are going to push right children into the stack. For example, when we are given this binary tree, we are given root of this binary tree, we'll begin from the 10, we'll process 10, we'll print it, right? And then we'll push its right child only. In the earlier solution, we were pushing right and left both, right? So we avoid pushing left and then popping it out in this solution. We push right child, then we simply go to the left child, right? Once we go to the left child, we print it again, push its right child, right? And then we go to the left child of it. Now what we do is we print left child 40, push its right child, and then go to its left child. Now when we are at 70, we do not have any right child, right? So first thing we do for 70 is we are going to print 70. Now we do not have any right child for 70, so we are not going to push anything. And when we go to the left child of it, our current becomes null, right? The current node, which was initially 10, then 20, then 40, then 70, now it becomes null. When it becomes null, it means we have gone to the leftmost for the current node. Now what we do is we need to process the right children. So what we do? We take out the stack top now. Now we take out 80 and we repeat the same process for it. If 80 has left, 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 we go to left, left, left. We keep on printing them and keep on going to the left side and keep on pushing their right children into the stack in this order. For example, here for 10 we have 30, then 50, then 80. Let's now see the working of this implementation for this tree. So what first thing we are creating is empty stack and we are initializing our current as 10. Now we have an outer loop. There's an outer loop in both the implementations, and this outer loop runs while current is not null or stack is not empty. If any of these two conditions satisfy, we keep running the loop. And inside this loop, what are we doing? We have another loop inside it. And this loop simply says that keep on going to the left, 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 keep on printing the items and keep on pushing their right children into the stack, right? So what are we doing? Print the current item. If right child exists, then push it to the stack and go to the left side, right? That loop just makes sure that you go to the leftmost side, right? And then you go to the null. Once you go to the null, it's going to take out the top item from the stack, which is the right child of the last processed node. So we initially begin from here, and after the first iteration of the outer loop, we will have 10, 20, 40, 70 printed on the screen, right? When we run first time, we will go into this loop these many times. We'll first print 10, then 20, then 40, then 70, and then we'll come out when 70 is left becomes null, right? And while we are processing these nodes, we must have pushed 30, 50, and 80 into the stack, right? These three nodes must have gone into the stack. Now when we come out of this loop, what are we going to do? We are going to take out the stack top. Stack top is 80. So we pushed 80 into the stack and then we took out 80 of the stack. So our current becomes now reference to or pointer to this node 80. So we again begin from here, right? We have printed 4 items, we have pushed 3 items, and then we have popped the top item. So we are again going to begin the execution for this node 80. And when we begin the execution, what are we going to do? We are going to go 80 left, left, left. While there are nodes, we are going to print those nodes and we are going to push right children. But for 80, there is no left, there is no right. So we'll simply print 80, right? And after printing 80, we'll go to the 80's left, which is null. So we'll again go to the else part. In the else part, what are we going to do? We are going to simply take the top of the stack, which is 50 now. Now when we take 50, we are going to print 50 on the screen and we are going to go 50's left, 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 and we are going to push 50 right children. But 50 has nothing, right? So we'll simply go to the null, 50 is left, and when we go to the null, we take out the next item from the stack, which is 30. When we take out 30 from the stack, what happens? We begin the execution again from the beginning once we have taken out the 30. And we run this loop, inner loop, which says that go to left, left, left while there is a left child. And keep on printing also and keep on pushing the right children. We do 3 things inside this loop, right? So there is no right child of 30, no right child of 60. So we'll simply print 30 and 60 and we'll not push anything into the stack, right? So we'll have 30 and 60 and 60 is left as null. So we'll have current as null. Now at this point, we have stack empty and we have current null. Both the conditions become false. So we come out of our main loop and we have printed pre-order traversal of the given binary tree. Time complexity of this solution is also big O of n. It's going to print every node exactly once. Auxiliary space required by this implementation is less because we only put right children into the stack. So we'll have at most big O of h right children when we are beginning with the root. So the space required for this solution is big O of h.